Welcome. On this video, we will discuss the idea of performing constructions with circles. So let's start looking at this introduction question, which states, is it possible to inscribe an equilateral triangle inside of a circle? So what do we mean by that? Well, to inscribe an equilateral triangle inside of a circle, all we're trying to say is it possible for us to fit an equilateral triangle inside of a circle? For that, we have this special construction, and the construction just follows two simple steps. To properly inscribe an equilateral triangle inside of a circle, our first step is to take a look at the circle that we're performing constructions on, and we're going to start by just measuring the radius of the circle, which this seems to be the radius of the circle. And now that we have properly measured the radius of the circle, what we're going to do is, with this same measurement, we're going to get our compass and we're going to mark. We're going to be marking our circle using the length that we obtain from the radius. So here we have one mark, and now we're going to get our compass one more time. I'm going to place it on the previous mark, and I'm going to see where's my next intersection. And again, we're doing all this using the same measurement of the radius. So we will do this one more time. And we're going to do this one more time until we go in a full circle. And again, we're all just using the same measurement of the radius. So there's another mark. Place it here. My next mark should be around here. And notice that we will complete a full circle here. So what we have done is, when it comes to our circle, we have properly have 1, 2, 3, 4, 5. We got 6 intersections using the measurement of the radius. And what we're going to be doing to properly inscribe the equilateral triangle, using the marks that we had here, we're going to pick a point. It doesn't matter which one. Let me just do blue now. I'm going to pick a point and I'm going to connect it not with the following mark, but I'm going to actually skip one mark and connect it to the next one. So that's one line. And I'm going to choose this point, and I'm not going to connect it to the next one, but actually I'm going to skip one. So that's my next one. And now using this point, I'm not going to connect to the next one, but I'm actually going to skip it. And now notice that what we have done here, we have created a triangle. And you can measure this. If everything is done correctly, this triangle is not just a regular triangle, but this is an equilateral triangle. In other words, all lengths are equal and all angles are equal. But let's think about, why is it that all sides and all angles are equal? But notice that what we have done here is we have cut our circle into 1, 2, 3, 4, 5, 6 arcs. So what we have done, we have created 6 equal parts. So we have 6 arcs, and they're all the same measurement since we use the same measurement. So we know that we have 6 equal arcs. Now, what is the measurement of each arc? The measurement of each arc is, in this case, will be 360, because that's a full arc. I'm sorry, that's a full circle. And since we created 6 of them and they're all equal, so we can divide that by 6. And therefore, the measurement of each arc is just 60 degrees. So I know that if I were to measure this arc, that's 60 degrees, that's 60, that's 60, that's 60, that's 60, and that's 60. So every single arc has a measurement of 60 degrees. Now, what is the actual measurement of this angle? Well, notice that this angle can be seen as the inscribed angle between these two lines, or between these two chords. But if this is 60 and this is 60, so therefore if we take a look at the inscribed angle, it's an inscribed angle of 120 degrees. So here we have an inscribed angle of 120 degrees. I'm sorry, it's meeting the arc of 120 degrees. And I know that there's a relationship between inscribed angle and its arc. And the inscribed angle, it's always half of the arc. So if the arc is 120, therefore, this angle must be 60. And the same idea can be applied to this angle here. Because this angle can be seen as an inscribed angle, and it's meeting two of those arcs. So therefore, my whole arc is 120, and the inscribe is half of that. So therefore, this angle is 60 as well. And the same idea can be said about this angle. Notice that this angle can be seen as an inscribed angle. It's an inscribed angle that is meeting an arc of 120, because I know that every single arc has 60 degrees. So therefore, the whole arc is 120. And therefore, the inscribed angle, it's always half of the arc that is intersecting, so that is 60. And now notice that this fits the definition of an equilateral triangle. Here we have completed a triangle with equal angles, and therefore all its sides must be equal as well. So this also answers the question, is there any relationship between the angles of the vertex of the triangle and its opposite arcs? And that relationship was that the angles are inscribed angles who are intersecting arcs of 120. Therefore, all angles must be half of it. Therefore, all angles must be of 60 degrees. So this is just a very nice construction. This is a construction that we use to show that we have an equilateral triangle inscribed, which means inside of a circle. But now, how do we actually perform constructions? Because notice that in the past we have talked about certain transformations. We have talked about the transformation of translation, reflection, dilation, and rotation. But how can we perform all those transformations with a circle? So let's just do one of those different transformations, and we'll talk about the main idea so you can actually perform the rest of the transformations yourselves. So now looking at example or activity number 1, here we have activity number 1, which says here we have a circle. Let's perform a translation. Let's perform a translation over the line CD of the circle whose center is A. So what we want to do is we want to get this circle and we want to translate it using this vector. So how do you actually translate a circle? Well, let's think about what do we use to define the circle? Well, to define the circle, we definitely need the center of the circle. So here we have the point of the center of the circle. And recall that to define a circle, we need two things. The first one, we need the center. And the second one, we need the radius. Because once we know the radius and the center, then we can define the circle. But what do we need to define the radius? Well, to define the radius, we need the center and a point on the circle. Because this way, notice that here we can say that, well, here's my center. And now my radius is just the distance of those 2 points. In order to define this distance, I need a second point. So to perform a construction over a circle, all we need is the center and a point on the circle. Once we have defined those 2 points, all we got to do is just perform the transformation on this segment, and the circle will follow. So let's perform the transformation on the circle. So in reality, all we have to do is just perform the transformation on this line segment. So thinking back at the transformation of a translation, remember that our first step was to just measure the vector. So this is the total distance that we want to travel. So therefore, using this distance, let me perform this vector on point A. So here we have A, and using the distance that we got on our vector, we're going to perform an arc. So let me just label this. This is my arc for A. And again, still using the same distance, we're going to do the same for B. So now this is my arc. Let me actually use the right colors. So here we have our, okay. So here we have our arc for B now. And again, recall that in order for us to actually define the location of the circle, our second step is just to, let me go back to here. I'm going to measure the initial distance that A had with the vector, and using the same distance, I want to see where it intersects the arc that we have just created. So that's about here. So I know that this point A, after it's been moved by this vector, this is its new location. And we're going to do the same for B. I want to measure the initial distance that it had with my vector. Let me actually change the color now. And again, using the same distance, I want to go back to the end of my vector, and I want to see where it intersects the arc of B. So I know that now this is my B prime. But notice that all we have done, we have translated this line segment. So if we get this line segment, and if I move it by this vector, this is its location. But notice that we didn't want to translate the whole, just a vector. We wanted to translate the whole circle. So all we have done, we have moved the radius of the circle. But once we have the radius of the circle, all we got to do is construct the circle using that radius. So therefore, this is the radius. So here's my circle. All we have done is we got in the circle, and we have moved the circle using this vector, and this is the image of the circle. So notice that all we got to do when it comes to transformations of circles, all we got to do is just perform the transformation on the radius of the circle. And at the end, we just got to create the circle using the radius that we got here.